Hello. In the last week, we have seen that plastic materials are not hermetic. That means by diffusion, water can penetrate through a layer of such protective material. I have made a sketch which shows this in more detail. We have a typical package. That package consists of a lead frame. The lead frame carries the chip. The chip and the lead frame are embedded into the plastic material, and now that package would be stored or operate in a water-containing atmosphere. So the relative humidity in air can be between 0% and 100%. Typical value would be 50 to 60%. And due to basics of physical chemistry, there will always be a certain content of water which is in equilibrium with the water in the environment. And so the plastic will always take up water. That water can come into the body of that package, so it is dissolved in the epoxy material, and it can penetrate, and it will mainly penetrate towards interfaces. So we can see here water at interfaces. And these interfaces now carry a thin layer of water, which is maybe only 1 or 2 molecules thin, but the water is there, and it can have effects both on the adhesion in the system and on the behavior of the package under temperature and temperature shocks. A second way where these humidity can come in is along the lead frames. Here we have an interface between polymer and metal, and that interface means in the polymer we have a disturbed region where more water can be stored and where more water can migrate along. So what's the effect of the water? The effect can be on the chip surface, for instance, a corrosion of the chip, especially of the metallization. We can have a degradation of the chip by moisture that penetrates in. Also, electrical properties could be changed just because water is conductive. Then there can be delamination of lead frame from plastic. We can have delamination of silicon from molding compound. And all of these phenomena are not desired. And we must keep in mind that the main barrier against water is this passivation, which is on the active area of the chip. But there is another effect which can be very detrimental, and that's so-called popcorning. Popcorning appears when we go into a soldering process, and what's the typical temperature of soldering? It's around 250 degrees centigrade, and that will have a strong effect on the water. But first, let's have a look to see how fast water goes into such a package. What is your idea? Do you think it is a matter of minutes, of hours, of days? Of course, that's depending on the temperature. The higher the temperature, typically, the faster the diffusion. So we wanted to know this, and so we did a small experiment. We took a package that is a TQFP64 package. And in that package, we installed a capacitive moisture sensor. And later on, the whole thing was bonded, wire bonded. We only need 2 terminals here because it's just a capacitor. And then we could go into a molding process. And here we wanted to know how fast it goes with the diffusion towards the chip. And the second question for us was, can we have additional barriers which slow down the diffusion of water towards the chip? And so that was our test vehicle. And here is the measurement. We measured the water concentration just as a change of capacitance over time. Of course, we know what the maximum humidity in the package is, because on the outside we set conditions of so-called 85-85 test. That's 85 degrees centigrade and 85% of relative humidity. So in such a test we can just achieve, let's say, a maximum water concentration here in arbitrary units, and here the maximum value would be 215. When we start here, we have, for instance, a dried package. So that would be 85%, and that would be 0% in the air. And of course, that also would be 85% of the maximum possible moisture uptake of that package. And in fact, we didn't know precisely how much it could take, but maybe it is 0.2% by weight. And so here that would mean 85% of 0.2 weight percent. When we transfer the package into the moist atmosphere, we can see after a small lag time an increase which is more or less an exponential increase. And here we can see the capacitance change over time is something like the initial capacitance plus the delta C max, which is this value, times a time-dependent function. And that time-dependent function is typically such an exponential function, 1 minus e to the power of t divided by tau. And tau is the time constant of our process. Where do we have the time constant? The time constant is typically for 63% change. Again, it's not absolute percent, but it's relative change. So somewhere here, let's say that's 187 to 15. That's roughly 30. So at 20, so roughly here is the time constant. And the time constant is, let's say, 260 or so minutes, so roughly 4 hours. That means after 4 hours, such a package is saturated in a moist atmosphere at 85 degrees centigrade. And that means it's a very fast process. As a rule of thumb, we can say with every 10 degrees centigrade, which we lower the temperature, this time constant will double. So you could say maybe at 65 degrees centigrade we have 16 hours or so. So at room temperature it's not so bad, but it's still a matter of days until we have saturation of that package. What we can also do is we can take Fick's law, and so Fick's law says the concentration change over time at a certain point is proportional to the diffusion constant times the second derivative of concentration from time. And when we integrate this over time with proper boundary conditions, we will again end up with such a function, and that function says something like the time constant is roughly p square divided by h square. H is the thickness here, times the diffusion constant to the power of -1. So the thicker the higher the diffusion constant is, the lower the time constant will be, and the higher the thickness will be, also the higher the time constant will be. So thicker means takes longer until moisture has been taken up. And in that way, such laws are built up, and we find very many different literature which ends up with such a function. Okay, but now let's come back to options to improve our system and also to try to optimize this barrier system. And now our idea was we make an internal barrier. So we take our chip together with our bonding wires, and we know the bonding wires are metal that is open to the humidity, and also the aluminum here around the bonding wires is open to humidity. And so we did first a coating which is a soft barrier layer and a hard barrier layer. And so the complete device after assembly was coated with these two layers, soft and hard. And such a layer can be silicon oxide or silicon nitride. Here we can see the two layers which are on the chip. One is the soft and the other is the hard layer. So what really seals is the hard layer. The soft layer is only to avoid cracks near edges or corners. And now we did the experiment I was showing previously. So we measured the uptake of humidity over time. And here we took a diffusion coefficient, which is just a relative change. And so we could say the relative speed of diffusion would be roughly 7 in the normal package, which has no coating. If we have an external barrier, which is just here, then we would decrease it down to 2. So that's external. When we have an internal barrier, which is inorganic, it is a similar effect. So it's more or less the same material protecting on the outside or the inside. On the other hand, if we take an internal barrier which has first a soft and then a hard layer, then we go down to, let's say, 0.6 or so, and here we are roughly 6.5 as a relative speed. So here we have roughly 2 and 2. And that means we can have a significant decrease of the moisture diffusion by a factor of 10 by very thin layers. Here we must say this layer here is maybe just 0.5 micrometers. And so you could say the 0.5 micrometers of such an inorganic layer are much more effective than the molding compound, which typically has something like 0.5 millimeter of thickness. So that means this investigation shows that such very thin barrier layers are very effective, and of course on a normal chip that is the natural nitride passivation we have here. So, first of all, it proves inorganic materials can be used to seal almost hermetically. And on the other hand, it shows that polymers are not very good at achieving hermeticity. We also measured the water vapor permeability at 85 tests. That means we just had a sheet of that material and we measured how many grams of water penetrate to a certain layer which has a thickness of 1 millimeter on one day. And so you could say through 1 square meter of molding compound, 5 grams of water will penetrate. On the other hand, if we take such a molding compound and we take silicon nitride here, then only 2 gram will penetrate per square meter a day. So I would say as long as polymers are involved, you never get absolute hermeticity, but you get a significant improvement. So moisture is a problem, and moisture can degrade adhesion. On the other hand, it is also a good point to think about adhesion in systems where we have polymers, and in the polymers, for instance, a lead frame of copper is embedded. And here we can say we made a certain test. The sample can be seen here. We pull in this direction because this strip in the middle is sectioned. Both strips can be pulled apart, and what we measure is the adhesion on these layers here. These define the shear area. So at least that's half of the area. And when we go back, it's very interesting. The adhesion will be a result of this chemical reaction between the polymer and the metal. And on the other hand, it also will depend on the intrinsic strength of the molding compound. The strength of the molding compound is very high. For instance, it has a fracture strength of roughly 140 megapascal at low to intermediate temperatures, and then it degrades over temperature. Also, the yield point is significantly lower, but still that's a little deformation in the material of 0.5%. Also, this yield point will go down. So we can say the polymer itself, it is quite strong. It's really strong, even compared to other materials like metals. And on the other hand, we measured this adhesive strength here. And here we made the experiment where we had different lead frame alloys. We had alloy 42, we had copper iron 2, and we had nickel palladium, which is equivalent to nickel gold. And as a function of these metal lead frame surfaces, we measured the pull-out strength, which is measured in Newton per square millimeter. That means the fracture force is divided by A. So you could say the breaking strength is something like F, and that is the force, and that's the area, and it's a shear test. Okay, we can say using this material, which is an epoxy, we have adhesive strength of roughly 7 Newton per millimeter square or megapascal. Doing this molding on a copper iron 2, we have almost 5 as an adhesive strength. But when we use a noble metal, this strength is significantly lower. It's only 2.5. So that's the strength after we just do the molding. Another question is, how will that behave after a certain time of operation? And here on this x-axis, we see different environmental tests we do. For instance, one test would be keep it at 180 degrees centigrade for 1,000 hours. What we can see here is the strength on copper iron 2 with nickel palladium will increase a little. The strength of copper iron will decrease. It's a similar behavior at 200 degrees centigrade. On the alloy 42, not very much will happen. That decrease is mainly a result of copper oxidation. Another test which is very important and which we have to address is, of course, moisture. And here, one of the most important ones is this 85-85 test. After 1,000 hours, the strength is still good with alloy 42, but it has increased significantly with all other surfaces. It's similar when we go into temperature cycling, minus 65 degrees centigrade up to 150 degrees centigrade, 500 cycles. And we can discuss why there is an increase. And one of the reasons is, under these tests, there is a certain shrinkage of the material, and that shrinkage will lead to higher clamping forces by the shrinkage. On the other hand, one of the most important tests, because it's relatively fast, is a pressure cooker test. That pressure cooker means like pressure cooking when you are cooking in the kitchen. You have a pot, and in that pot you have boiling water, and over the water the sample is stored. Because this pot is closed, a higher pressure of roughly 2 bar will build up, and that leads to the fact that the temperature which we reach here will be roughly 120 degrees centigrade. And that's a very hard test. And this test is able, in order to test molding compounds or packages with molding compounds in a very efficient way. Here we can see, against the other testing conditions, there is a certain decrease of this adhesion of the lead frame material against the molding compound, but still the residual strength is high enough, and so we can say such a molding compound has been qualified by such a test. On the other hand, when we look at the packages, I said that package is saturated in some way with humidity, and humidity will be found especially in interfaces here. The interfaces are weakened, and also when we go into a soldering at 250 degrees centigrade, this water will evaporate, and the pressure it will build up will be very high. So maybe if every 20 degrees centigrade the pressure increases by a certain factor, then we can see there will be a very high internal pressure on the packages. And that internal pressure will lead to bulging, or it will lead to cracks on the package. And of course, that is a severe damage to our package. This effect, because the device becomes a little bulged, is called popcorn test. So, you know, if you have a grain of corn, putting it on a hot stove plate, it will pop up in some way. And in a similar way, it happens with such molded packages. The molding compound saturates with water. Water is mainly at the interfaces. During the soldering of the device on the board, the water suddenly evaporates. Internal pressure will be high, and it causes stresses, and it blasts the plastic package. So that means we have some damage here. And so popcorning has to be tested. And the idea behind the test is the following. We define a so-called popcorn sensitivity level. That level can go from A to 6, and that level defines how long you are allowed to expose it on a typical fabrication floor. For instance, if you have in your fab temperatures under 30 degrees centigrade, but 85% humidity, that could be somewhere in China, Southeast Asia or so. And when you are able to keep this package for infinite time in such atmosphere and without coming to popcorn effect afterwards in soldering, then the package gets the best level, which is level 1. If you have other conditions, for instance, below 30 degrees centigrade, but in a quite normal atmosphere, 60% relative humidity, that could be here a non-climatized lab in Europe. And if you can keep it for 4 weeks, then it's level 2A, and there are intermediate levels. If you can keep it only 24 hours under these conditions, then it's level 5A, which is a relatively bad level. What's the idea behind this? Typically, manufacturing machines for pick and place, they are loaded from a magazine, and often standard devices stay in that magazine overnight. Yeah, for instance, a certain microcontroller or some logic IC. So if you keep it overnight and for more than 24 hours, and you have only popcorn sensitivity level 5A, you could expect that later on you will have popcorn effects. The worst case is if it's below 24 hours and if only a certain time is given on the label. Of course, when you produce packages, you want to have a accelerated testing, and that accelerated testing would mean, for instance, you make the test time shorter by increasing the temperature. For instance, for level 1, you go from 30 to 85 degrees centigrade. The humidity is maintained, and you keep this for 168 for 68 hours. And if after that, in a soldering process, this whole procedure is survived, you get level 1, or you have a non-accelerated test for the lower popcorning grades, and here you have no acceleration, and that means you have to test for a very long time, but there are certain alternatives to make this test faster. For instance, if you want to go from 700 hours to 120 hours, you can increase the temperature by 30 degrees. Of course, when you do this testing, also the soldering process is part of the testing procedure. And that means the standard which describes a popcorning test also describes how you have to perform the soldering. For instance, in tin lead alloys, it describes the time at temperatures above 183 degrees centigrade, and in your test, this time must be between 1 and 2.5 minutes. The time near the peak temperature, that is the highest temperature you can measure in your oven, must be 10 to 20 seconds. And the peak temperature range is either 220 plus 5 minus 0 degrees centigrade, or 235 degrees centigrade plus 5. That's depending on the solder alloy, whether you have a tin lead alloy or if you have a SAC, tin silver copper alloy. The cooling rate must be somewhere up to 6 Kelvin per second, and that means all of the conditions of the soldering are well defined. This is so-called infrared or convection soldering, so that uses radiation or it uses hot air. On the other hand, you have a so-called vapor phase soldering. There you put your devices into a certain gas atmosphere, and these gases, they have precipitation and condensation at 215 or at 235 degrees centigrade, and that is so-called vapor phase or condensation soldering. Okay, the last thing which has to be defined is what is a failure. So you have to ask yourself, when is an electronic device failed? There are many criteria. One of the criteria is the device is dead. So it's an electrical or functional failure. Not necessarily the device is not working at all, but it just could be the characteristic curve of the device is no longer according to specification. So you could say that is either dead or it is out of spec. On the other hand, you also have visual criteria. Nobody wants to have a device which is cracked on his printed wiring board, even if the device is still functional. So you do not allow outer cracks, which are visible with a small microscope. You do not want to see internal cracks, especially such ones that cut a bonding interconnection or some conductor contacts. There are other so that typically would be an electrical open, of course. You have different kinds of internal cracks that begin at package elements, for instance, at the lead frame or the chip. And you have bending, swelling, buckling, which are visible without technical support. So if it's really popcorned, you don't have to accept this. So in that way, we have defined the popcorning phenomenon. On the other hand, we have seen how that complex phenomenon is induced. And on the other hand, we have seen how we can test for popcorn sensitivity. Making devices better is quite complex because it involves your molding process, it involves the design of your package, and it involves the proper selection of the molding compound for your individual device. Generally, we can say bigger devices are more endangered than smaller devices. Okay, maybe finally, to finish with plastic packaging, I would show you a different process compared to reactive transfer molding. We see here a ball grid array package, and what is important, it is first the interposer. Interposer is typically something like a printed wiring board of high quality. Typically also it has, for instance, nickel gold surfaces, because you want to wire bond. You pick and place the chip. We harden the glue. Oh yes, first we deposit glue. Then we wire bond. And then we could go into a molding machine. But if we want to produce only a small series, or we want to produce just a prototype, for instance, we would like to just to test a new control unit for automotive tests. So we do not need 1 million of ball grid arrays, maybe we just need 50 ones. And so building a molding tool for only 50 devices would mean we have to spend 100,000 euros for 50 devices, and that would mean 2,000 euro for devices just for molding. That would be too expensive. And to that purpose, people have found an alternative method. We take a syringe, and in that syringe is a liquid molding compound. In fact, it's not called molding compound, but it's a so-called glob top material, but it's a molding compound that is liquid at room temperature. Then we deposit a ring of that material here around our chip, and then this ring is filled up with a complete layer of our glob top material. So we deposit, and then we harden. Advantage is no tool, and all of the design is software designed. Yeah, why is it so? That machine we use for deposition, that can be some kind of automated machine. Here we see the syringe. Here is our vision system. That's a camera and illumination in order for the system to detect where the proper position of deposition is. That complete system is programmed from a personal computer. Here we see such a deposition head for this pasty materials, and so this moves zigzag over our chip, and in that way we can do a coating. Such a machine is relatively cheap, so you could say having such a machine costs no more than a tool, or typically less than a molding tool we use in production, and that machine can be programmed for any deposition purpose we have in assembly and packaging, depositing glob top materials, depositing adhesives, depositing solder pastes, and depositing sinter material. And in that way, we have a so-called digital process. All of the geometries and so on are defined by some software package. So we define the interposer that is just delivered from a printed wiring board company. We pick and place the chip with a free programmable machine. We have deposited the adhesive with such a syringe machine, and finally we coat it. Maybe one last step which is a little more demanding is the balling, but again that can be achieved in an easier way. For instance, we have our ball grid array body, and then we put on a sheet material which has many holes, and in these holes we deposit solder balls. These are sticky to some resin material, and then we transfer the whole assembly through an oven, and in that way we melt the solder balls onto the solder pads. And in that way, you could say everybody can build his own ball grid array. Okay, and that's it. And in that way, we have also the possibility to produce plastic packages on small scale and to have them quite easily and fast available. Okay. Thanks for your attention.